This modified Delta 3D printer can now work through a print queue autonomously, ejecting parts automatically when done. Today, I'll show you how I created a 3D printer that can print by itself forever, or at least until it runs out of filament. Simple to explain, but a long time in the making. Converting a 3D printer to have a conveyor belt bed so it can automatically eject finished parts and process a print queue by itself. There's a lot to cover, so we'll jump right in by looking at the inspiration for this project. A while back, I proposed a 3D printer called the 3D Farmer with a belted bed so it could automatically eject parts when they were done, ideal for a print farm. I wanted to have a 3D printer like that after testing the Creality CR-30. As I loved the way it could automatically eject parts, but I didn't like the compromise of the 45-degree printing angle. Traditionally, if you're printing many parts at once and one of them goes wrong, it's going to knock off the others, resulting in an epic failure. Whereas with the conveyor belt, you can print these parts individually, one after each other, but even if some fail, the rest are unaffected. There's been a lot of development in belt printers since the Creality CR-30 was launched, and the iFactory one, which was launched around the same time. There was already the commercially available Black Belt 3D, as well as the open source White Knight, with new models since then, including the SaneSmart Infi 20 and the PowerBelt 3D Zero. You can also get kits to convert your existing 3D printer, such as the Ender Loop for the Ender 3, and the Additiva Belt 3D printer kits, again for the Ender 3 and the Artillery X1. All of these still use 45-degree printing, but there are other options. We have conversion kits, such as the one from Robot Factory in Italy, that replace your bed slinging Y-axis with a conveyor belt instead. This means you can eject parts when done. A similar design comes from Infinity 3D, who previously had a campaign on Kickstarter, again replacing the Y-axis with a belt, and as a bonus, giving the ability to eject parts when done. This particular model interesting because it can be converted between 90-degree traditional mode and the angled 45-degree mode. Another interesting option is Print Shift from Paul Chase, designed for the Prusa Mini, and positioning a belt around the existing Y-axis and bed. When the print is done, a very clever coupling system is used to rotate the belt and eject the parts out the side. Beyond belts, there are other solutions, such as this system from Make Anything, which relies on the part naturally cooling and then being pushed off by the print head, allowing automatic part ejection. Similar systems, such as Quinley from 3DQ, are designed to turn existing printers into print farm capable machines. And then we have a similar system from AutoDrop 3D that introduces a traditional wiper to remove the part rather than relying on the print head. Last but not least, Tom Sandladerer had an ingenious system that used actual print beds on his Voron 2.4. This is a really novel idea, with the only compromise being a reduction in printer volume and the need to manually reinsert the beds. There's so much clever thinking out there in the community, but my goal didn't quite match any of them. Obviously my primary goal is automatic part ejection, but I want a traditional perpendicular nozzle because I don't like the compromises that come with an angled print head, and that includes having to use a specialized slicer. I'm happy to use a belt, but I don't want X, Y or Z movement affected by it. Furthermore, I don't want to lose any build volume. For this reason, a Delta printer is perfect because the bed is stationary and a belt can run over the top. In fact, I accepted reviewing the Super Racer with this project in mind, and the Clipper conversion was leading towards this too. Finally, I wanted to be able to queue multiple prints without changing the G-code myself, and I wanted to finish the project in a way that was open source, with easy to buy parts for anyone else building along with me. This solution, in my opinion, ticks all of those boxes. So how did I design it? You should understand that I completed this project, designing it piece by piece as I went, experimenting with packaging options, and trying to use parts that I already had on hand. A lot of effort was needed at the start to model the mounting points for the bed, as well as the extrusions that make up the corners of the Delta frame. This gave me a nice foundation to base my custom parts on. When it came to the V-slot lower frame, I tried to work smarter rather than harder, using this beam plugin for Onshape. As you can see, it's got many profiles available. We simply select what we want, provide it with some straight lines that the beam will be extruded along, and then have it automatically create the required extrusions without modeling any of the small features. If you also use Onshape and you think this looks handy, you come down to Add Custom Features and then paste in the URL that I have in the description to install the beams feature. Because of my design as I went approach, I had a problem that required a design change halfway through. The original belt path used 3 idlers to create space for the power supply under the machine, but the mounting lugs on the existing FLsun bed intersected with the top of the belt path underneath and required a change. The new design only had 1 idler roller, giving a simpler belt path, but did require the power supply to be mounted on the side. Because of this, you might notice in the footage the additional rollers are sometimes in view, and the parts still contain the mounting holes for the old rollers. I've also updated some parts since filming, so expect some changes there. To build this, you will need additional hardware, starting with a belt. Some time ago, I was contacted by Adam from PowerBelt 3D, creator of the PowerBelt 3D printer kit that we saw earlier. He wanted to know if I'd like to test the belt that they developed for the Creality CR-30, which apparently had been through 32 iterations over 28 months to get it just right. Adam also offers custom belts to your length and width, which I purchased as the first step in this project. The width of 280 was designed to just fit within the tower and cover the bed, but the length I purposely ordered too long, knowing that I hadn't designed the machine yet and I'd have to trim it down later. The exact specs of the belt are provided in a bill of materials that also includes all of the printed part quantities as well as all of the hardware needed for each step. It has links to buying parts on Amazon, as well as where I got the parts locally in Australia. The lower frame is made up from extrusions that I had lying around, and I settled on 2040 for the size. 5 lengths are required, and only one of them for me had to be trimmed down, as 450mm was the length of what I already had. To put together the frame, you'll also need 6 corner joiners of your choice, and the rollers are based on what should be easy to get, PVC plumbing pipe. This is listed as 25mm, but it's actually a little over 33 external and just under 30 internal. In North America, this should be nominal pipe size 1 inch with a Schedule 5 wall thickness. Through the middle of the rollers is M5 threaded rod, and this is supported by MF69 5ZZ flanged ball bearings. The belt system is driven by 2 stepper motors and then a series of 2 GT pulleys and a closed loop 188mm timing belt, and there's a pair of these on each side of the drive roller. All of the hardware is listed in the bill of materials, but it's largely M5x12 bolts, some M5 nuts and lock nuts, matching M5 washers, and then of course M5 T-nuts to go into the extrusion. You'll need 4 compression springs to mount the bed plate. I wish these ones were a bit stiffer, but they do work. For the underside of the frame, you'll need some rubber feet. Stick-on is fine if you can't find these bolt-ons. The hardest part to source is this plate that I milled from 3mm aluminium. My CNC router in the garage was up to this task. If you don't have access to this, you could laser cut this piece from any rigid 3mm material that can handle the temperature of the nearby heated bed. Apart from that, everything else is 3D printed, and you might have noticed me printing all of these parts in a couple of my recent videos. PLA is fine with 50% or more infill for strength, and only one of the parts requires support material. Everything is modeled the perfect size for me, but you could always tweak the source CAD to suit any variation in the parts that you use instead. The next part is the disassembly of the old printer and the assembly of the new parts. This video was going to end up way too long, so I'm releasing a separate build video tomorrow to keep things concise. In terms of this video, we're going to continue by looking at the firmware and software changes needed to make this work. On this printer I'm using Clipper firmware, partly because of the manual stepper feature, which is absolutely perfect for this application. We paste the example into our own Clipper configuration, renaming the manual stepper belt and adjusting the pins to suit our main board. The other values I settled on after some trial and error. Assuming we're using a 2209 stepper driver to match the rest, we also need to add in a section to reflect this, and to avoid errors we need to match the name, in this case manual_stepper belt. Our final component is a simple macro, using the manual stepper G code for the belt stepper, resetting the position to 0, and then moving it forward, in my case 400mm. I also opted to add this macro to the LCD using a custom menu item, which I've covered in detail in a previous video linked below. Also linked below is the full printer configuration posted to my GitHub. That's it for now with firmware, but once the belt is installed, you'll need to run PID Auto-Tune for the bed, and you'll also need to rerun the Delta Calibrate Clipper procedure to map out the new bed position, as we've gained around 50mm in vertical build volume. Once this is done, the new values will be stored in the bottom of our configuration file. The reason I'm using Octoprint is so I can use this continuous print queue plugin. It's recently had a change of developer, and with that have come some new features. These features are actually more than I need, because in my case I just need to add my eject macro to the bed cleaning script as well as the queue finish script. Finally, the slicer, and there's not really anything that needs to change here apart from one thing. I've increased the thickness and the height of the skirt to make it chunkier and more robust. Before I made this change, I had some incidents where it was too thin, still stuck to the belt, and got sucked down in the gap at the front. On paper, everything was finally ready to go, so I just needed to install the belt and do some printing. To assist with belt installation, PowerBelt 3D supply a tutorial video on their website, explaining that the joining tape is pressure sensitive, so you can work methodically to attach one side tightly, followed by the other. I replicated this process, wiping off any fingerprints with some paper towel and IPA, before applying a strip of tape to one side of my belt, applying pressure from the center outwards but peeling back and removing any air bubbles as necessary, and finally introducing the other half of the belt and following the same process to attach the tape to it. To finish up is an easy job by trimming off the excess tape from either side, which means we're ready to tension. With the system built into my modification, this was quite an easy job. Righty-tighty to pull that corner towards the front, and all I did was monitor the tension by tapping up and down on top and making sure it wasn't too floppy. I also found it handy to run my eject macro during this step to see how the belt was tracking under movement and make any final adjustments to keep it centered. The rear roller brackets have oversized holes in case you need some fine adjustment there too. Using a combination of these various tools, I was able to get the belt tracking in the center and reliable. After all this work, I was pretty nervous when I started my first print, and unfortunately the nozzle was way too close to the belt and started running into it as I scrambled to adjust the baby stepping. When the cube was finished, it was really stuck, and I was worried that I had destroyed the belt underneath, but as I ejected the part, I found that it still peeled off quite nicely. And furthermore, while there was evidence that I had printed too close, the actual belt seemed to be undamaged, so that's a tick for its durability. At this time, I designed, printed and fitted these wedges to go on the front, just to aid with part removal cleanly from the belt. The idea is to slide it as close to the belt surface as you dare. With this in place, the ejection system was working quite well, and no longer needed my hand there to catch the object. Shortly after, I fixed up my first layer, and started to test the continuous print plugin some more. Here you can see the print is finished and the macro to eject is activated automatically by the plugin. The belt turns, the part ejects, and then we notice afterwards that the printer starts heating up again by itself, and soon after commences the next print in the queue. This plugin is perfect for my application because it's so flexible and easy to use. Even after you have a queue running, you can still add other print jobs, change quantities, and make adjustments. It works, so let's evaluate the system overall. I'm happy to say that as far as I'm concerned, I managed to tick a box for all of my design goals, and I even gained some build volume on the Z-axis. As a test of faith, I set up a queue of 6 items and went to bed, leaving the printer unattended. The next morning, I was anxious to see if it worked, but I was very pleased to find this time lapse that showed all 6 items printing and ejecting autonomously. So clearly, the system inherently works, but that's not to say that there can't be some improvements. It's very subtle, but I've noticed that the part can move very slightly on the belt during printing, so I might need to play with tensioning some more. There's also the tape where the belt joins. You can print on this, but it is slightly thicker and it's going to leave a mark on the underside of the first layer. Earlier on, I showed you that thin objects, if ejected too fast, can wrap around the belt and then jam in the crack at the front. I slowed down the belt speed, but I think a future improvement will be to add some fans to the side to cool the part and increase its rigidity before it reaches the end of the belt. So far I've tested this by using a hairdryer set to cold, and it works really well. For taller parts it's not really a problem, but I will add some cooling to make the system more reliable for skinny parts. If you want to build this, everything you need to recreate this mod is available on Printables. And please use the comment section below to give me some feedback and suggestions. This isn't a mod that I needed, but I felt compelled to design and make it simply because I wanted to, and in the end that was satisfaction enough. Thank you so much for watching, and until next time, happy continuous 3D printing. G'day, it's Michael again. If you like the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.